Okay. Up on the board are things which at the beginning don't seem very relevant to what we're doing, but it turns out they are what people found out helps understand what's happening. What's happening is that in this case, and there are 4 cases involved, in this case, what we have is a point and a line, and the line is at a distance d, and the line is vertical, and so it has the equation x equals x naught plus d. But it turns out that once we work on the thing, the x naught turns out to be not so important in terms of basing things on with the equation it results. It's important because it turns out to be the first coordinate of the focus, and the focus is the whole point, the focus and line, but it turns out not to be appropriate to keep that x naught. It's appropriate to change it. And the way we change it and, is to define an h and a k, and an a and a b and a c. And so now I'm putting this stuff up here. I told people who, one more person here, what I said to people who were here a few minutes early, I came extra early to write a whole bunch of stuff on the board so we wouldn't have to take time to do it now. The trouble was that the room was locked. The room hasn't been locked since 1990, and therefore we had problems because we don't have keys. Anyway, so it took 25 minutes for the person to unlock it, and that's why I don't have as much on the board as I would like to have. In any event, what we're talking about is that we have a point and a line, and we have some other point, xy, and the whole idea of it, and this is a bad point in terms of what I'm talking about, is the idea of it is the distance between the point and a given point is less than the distance between a point and the line. Now, for the point I chose here, that's not true. Okay, obviously this distance is bigger than that distance, and so the fraction of this is a numerator over that with a denominator would make a number bigger than 1. So this is not on the graph, but you've got the idea. What we want to do is figure out the equation based on the distance between the 2 points equals the eccentricity times the distance between the point and the line. Now that's not how it's defined. How it's defined is to have the distance between the point and the line be in the denominator, but once you put it in the denominator, it makes a fraction. When you clear the fraction, this is the equation you get. And so you start out with x naught, y naught, and d. When we get done, most of that is not going to be of something you see, because we're going to make some changes based on these numbers things over here. Now, there are 4 cases involved. There's also the case where the point is on the other side of the line, and then there's a case where the directrix, this line, is horizontal instead of vertical, and that brings in 2 more cases. I'm only going to do 1 case because you should be able to see how to change it when we change cases. Anyway, we started doing this yesterday and we got stopped by time. When I square both sides here, I get x minus x naught squared plus y minus y naught squared. Over here, I'll get e squared, and the distance, the absolute value squared, just gives me x minus x naught squared, because I'm going to put the x and the x naught together, plus 2 e squared x minus x naught d. Sorry. Let me write this better so you see the way I'm parsing it. It's this squared minus 2 times this times d, and plus e squared d squared when you square the right hand side. Then, and again, when you look at like 8 cases, because we're going to have 4 things like this for ellipse and 4 things like this for hyperbola. And when you look at the 8 cases, they're very similar down to a certain place. And where they change is where we bring in these things over here, because these things over here change. Okay, but down to a certain place, it's the same thing. So when you look on my notes, you'll see the same derivation for a while, and then we'll bring in something different. Anyway, we're not there yet. So what I notice is on both sides, I have this. And so I'm going to take them to the other side. I have 1 minus e squared times x minus x naught squared. And that takes care of those two. I'm going to bring the minus 2e squared d x minus x naught over to the left-hand side. And I'm going to bring or leave the y part alone. That's y minus y naught squared equals e squared d squared. So all I did here is bring 2 of the things on the right-hand side over to the left-hand side. Now I want to divide by 1 minus e squared. So I get the x minus x naught squared by itself. And you'll get minus 2 e squared d over 1 minus e squared. Kind of a mess. I'll have 1 over 1 minus e squared times y minus y naught squared. And I'll have e squared d squared over 1 minus e squared. Now, this is getting kind of messy. So it is at about this stage that we start bringing in this stuff over here. Now, the stuff over here didn't exist when people started doing this. They got this far down and they thought, well, what in the heck can I do with this thing? All right, well, if I want to complete the square, see, I have this thing squared minus 2 times some stuff times this thing. I might be able to make a square out of this by completing the square. Now, so this thing is kind of messy. So what I want to do is when I look at it and I look over here, I have e d 1 minus e squared. Now over here I have e squared d 1 minus, okay? But I also have c is ae. Now, just if I think about that a second, what is ae? Well, if a is ed, then ae is e square d over 1 minus e squared. So if I look at these two things, put them together, I get this. So this is c. So the point is that somebody noticed that this thing right here, I'm going to replace with c. Okay? So I have x minus x naught squared minus 2c times x minus x naught. Now how do you complete the square? Well, you complete the square by taking half of the coefficient, and this is the unknown right now, the x minus x naught. So half of that is just c. So what I want to do is add c squared to both sides. And if I do that, I haven't changed the y stuff. But on the right-hand side, I have e squared d squared over 1 minus e squared. That's something like this stuff over here. And so what I'd like to do is to figure out what this one is. I made this one look simpler. So the next step is going to say this is x minus x naught minus c quantity squared. Plus, now I've got 1 over 1 minus e squared. That's still kind of messy. Y minus y naught squared. And over here, I want to see what to do with that thing. Well, what is b squared? B squared is e squared d squared over 1 minus it. That's that. So this becomes b squared plus c squared. But b squared plus c squared turns out to be a squared. So somebody clever, you see, in trying to figure out how to deal with this thing up here, make it simpler so they understand it better. You define some stuff, and as you do that, you create this wall over here. Now, because I know it's going to be the same because it goes through it every time, once you see how to simplify it, you start out with this. And this is not clear to people what in the heck you're doing here, but when you get down to this step, it sort of becomes clear how that stuff fits in here. Okay? So b squared plus c squared is a squared. All right? This is a squared. So, and by the way, why is it that? Well, if you square b squared and c squared and add these two together, here's what you do. B squared is, b is a times the square root. So b squared is a squared times 1 minus e squared. If I take out the a square, I get 1 minus 1 minus minus, so I get plus e squared. And so what I get is a squared e squared, which is c squared. So that's the proof of this statement right there. And basically now I'm going to divide by a squared. Now it's going to turn out that I want to combine the x naught and the c here. I'm going to divide by a squared. And over here, I'm going to have 1 over 1 minus e squared and 1 over a squared y minus y naught squared equals 1. Yes.
Are you recording?
Do I what?
Are you recording?
I thought I was.
Sorry.
Am I recording?
Yes, you are.
Oh, thank you.
Okay. I didn't hear that part.
Oh, somebody wants in. Hello, come in. I'm opening the door. Okay, so we have just a little bit to do, and that is to see what this is. And when you play with that and this, you will find out that this is y minus y naught squared over b squared. I have x minus something. Now, if I look at, and I've got some problem here, I see, and I don't know where the mistake was made here, but there's a little mistake made somewhere with the, okay, this should have been, yes, I've made a little mistake here in the sense that this right-hand side, okay, when I square it, what happens here, I had a plus d, but when I write the x minus x naught together, it's a minus d. So what this is, should be right here, should be a minus. Did not mean to do that. That's why I wanted to write it down ahead of time. When you look at all these 8 cases, this is how they differ. Some of them will have a plus here and some of them have a minus here, okay? I didn't mean to make that mistake, but it's good to point it out because that's where we're going to make changes in a little bit. In any event, because when I put these together, it makes a minus d. When I square things, I get a minus there, which means when I bring it over here, I'm going to have a plus. So that's the second place if you're, well, third place. This is a plus right here. This is a plus. So this should be a plus, and that makes this a plus right there. And that makes this x naught minus c, and x naught minus c is h. And so in the end, what we get in this case is x minus h squared over a squared plus y minus k squared over b squared equals 1. That's what we get in this case. It's case 1 is when the directrix is vertical and to the right of the point. This is what we get. Now, notice you have an H, a K, an A, and a B. None of that occurred with the X naught, Y naught, or the D. We've lost the D, we've lost the X naught, we've lost the X naught and the Y naught. We replaced them with H and K and A and B. Okay, so what is going on? Well, I've got to erase something to do something here. If you look at this little picture, the x naught, what I've got here is this is the horizontal line that goes through the point perpendicular to the directrix. So the point that this line right here is that line over there. And all I need to look at is the same height. This is x naught, and over here is x naught plus d, because the distance here to the between the focus and the directrix is d. So, and so forth. Now, what's the c? If you look, the h is x naught minus c, and it turns out what the c is, I don't know. I mean, I know it's this, but the point is I'm subtracting c off of that to get h. Now, there's also a that comes in here, and what you learn is that c is less than a, and if this is c and it's less than a, that makes sense. The b is also less than a. You don't see the b here in this situation. I'll show you the b in a minute, but where it is, but you don't see it here. Okay, and so anyway, by making these little changes, you make a nice thing here. And what else? Well, if I just stare at this equation up here, we want to notice that the a is under the x and the b is under the y. The h and k turn out to be the center of something, although we don't know that yet. Okay. Also, if I look at this point right here, it's going to turn out that the graph is going to go through it. So the point x naught, h plus a, y naught. And when I do this, I need to change the y naught to k. This is y naught here. When I wrote it up here, I wrote k. That's because y naught is k. So I didn't say that, but I meant to say that. And anyway, if you stick h plus a y naught into this formula here, what will happen? H plus a stuck in for x is h plus a minus h, that's a squared over a squared is 1. Over here, the second component is still just k, that's 0. So you get 1 equals 1, and that's a proof that this point is on the graph. Okay, so when we start out here, this point I've said to people who were looking to see if anybody else is out in the waiting room, this point's not really on the graph because in this circumstance, this distance is supposed to be less than this distance. So I'm going to erase that and say, well, that's not a point that might be on the graph. But if I had less distance here and greater distance here, that might be a point on the graph. In any event, one point that is definitely on the graph is a point that has coordinates a distance a away from h. Well, when I have my original picture here, you don't see h. H is back here somewhere. So h is going to be back here somewhere, and k is going to be up and down, but that's the same thing. I got something back here. I've got this. This is the focus. We're going to call this the center of something. The distance between here and here is a, the distance here. And we just showed that this point is on the graph. Okay, that's one point that's on the graph. Now, we can also show that if I would take h, and what I did here a second ago is we took h plus a. Now suppose I take h minus a. Where is h minus a? Well, my problem is, of course, I don't have room to do anything here. If h plus a is that distance, H minus A is going to be over here, further. It's going to be an A distance away from H again. Okay, A plus A, H plus A and H minus A. The H is in between, and this is over here. If you plug that point in to the same thing, if I put H minus A in for X, I get H minus A minus H. That's minus A squared is 1 when I divide it by A squared. The other one is still 0. So I have another point on the major axis for an ellipse. That's kind of a surprise. Okay, when you're just working this out, you see this picture, and what did we do yesterday? We talked about parabolas. Parabolas are like this, they don't ever come back together. So when you study the parabolic case first, you're not surprised to see this picture of this thing being, like this, except, boom, this point's also on the graph. So that doesn't make much sense in terms of my picture unless this thing must come back around. And we don't know that yet, but you can verify this point's on there, fine. And we're going to do something else. If we go up a distance here, B, we go up B distance. If instead of the height here, if I do H, if X is H, this is 0. And if I go up a height B here, that's going to see what's going to happen. The height here, this would be the point H, K plus B. If I go up K plus B and put K plus B in for Y, K plus B minus K is B, B squared over B squared is 1. So it turns out I got this point on the graph also. And if I go down minus B, I'll have this point on the graph. And the B is less than the A. And so we're going to get something that's longer this way. I'm sorry I'm covering over stuff, but I don't have much choice with the screens. Okay. So it turns out that ellipses are what you think they are. I mean, you know about elliptical orbits and stuff from other places. The point is that we can plot points, we can do lots of stuff and verify that we actually get this kind of a blimp or dirigible or whatever looking picture, football, whatever you want to call it, something that is like that kind of shape, because an elliptical shape is kind of a hungover circle. Okay, and it turns out that if we would go over another distance here, there's going to be another directrix. In other words, we can show that there's another thing over here, that this point becomes a focus for another directrix. And so an ellipse turns out to have 2 directrices and 2 foci, although we didn't start out that way. Okay, that's in one case. What's the second case? The second takes place the point over on the other side of the line, and that's going to change this derivation just a little bit. As I said, it's going to turn out now that we're going to have the x naught plus c is going to be h instead of x naught minus c. And if you think about it now, because of what we just said, if you look here, this is the second case. The second case is to have this on the other side of that. So it turns out that we could go further with the first case and find the second directrix that's over here, and then the points over there, that will take care of case 2. What I chose to do in the notes is to start over by saying, okay, suppose I have a line and a point over there, do the same stuff here. All that's going to do is put everything over the other side. That's going to change a couple of these signs. And so instead of plus, we're going to have a minus, and then we're going to have an x plus c here. And that's okay, because that's how we're going to redefine h. And so if you look at these cases, you will see that they all come together. And so instead of doing all that, I'm going to erase this here now. let's talk about what you get. In the two cases that I just talked about, you will get x minus h squared, y minus k squared, an a square and a b square and 1 and a plus. This is the equation of an ellipse when the directrix is vertical, and when you do case 1 and case 2, you get the same equation. Because as I said, when you get this worked out, one directrix is over here, one directrix is over here, one focus is with there, and one focus is here. And the HK turns out to be halfway between things, and that's why it's called the center. Because you have a point up here just as far as down here, you have a point here just as far as here. This has to do with the A, its coordinates not A, it has to do with the distance A from the center. This is a distance C from the center. This is a distance C that way, and this is a distance A that way. So the point A, the point at distance from the center at A along the horizontal line is a point on the graph. And if you go up the other B thing, you get points on the graph. And that is why we like this equation for the graph. Because although it didn't start out, we don't see the eccentricity here, we don't see the D, and we don't see the x naught, y naught that we started with. But we get something that we can easily graph. Sum of squares, it's like circles. It's almost like circles, except these numbers, by the way, if they were equal, would be a circle. All right? If a squared is b squared, I can multiply, and I get this square plus that square is a square. That's a circle, radius a. So ellipses are like circles. Now, we only did two cases. What happens if I say, okay, now I want a directrix and I want to focus here, or I want a directrix down here, because now we know there's going to be two of them. Okay? We do the same game, except now we make this thing vertical. So what I'm doing is switching the coordinates. Okay? When you do that and you work this whole thing out, that's called cases 3 and 4 in the notes. When you work that out, and the stuff I erased is very similar. There's just a couple of places where there's minuses instead of pluses or vice versa. What you will get is x minus h squared over b squared plus y minus k squared over a squared equals 1. And the a is bigger than the b. So if I had x squared over 16 plus y squared over 9 equals 1, what do you know about that equation? First of all, it's an ellipse because it matches one of those two things over there. In fact, it matches both of them because they look the same, except one has a squared in the denominator and one has, and so forth. I switched the letters a and b, but they're both squares. I've got 16 and 9, they're both squares. When I look at this one, is it going to have a shape like this, or is it going to have a shape like this? Well, remember that the number A in the development is bigger than B. Okay? In this development here, I haven't changed it. All four cases have this going on, except the H changes and the K changes. That's the only thing that changes. When the bigger number is under the X, it looks like this. Because this distance across here is going to be 4, and this distance is going to be 3. Because I just told you this is A, and this is B. So when I see the bigger number under the X, that tells me it's going to be like this. If I had the bigger number under the y, it would be like this. Because in this case, you would go A this way and B this way. Okay? And so please look at that. This is what I did in case for the eccentricity being less than 1. Now, once you know that, we're going to do hyperbolas next. Okay, you got to start over again. But this time, the eccentricity is bigger than 1. So that's going to screw up all this stuff here. Because if E is bigger than 1, then the square root is imaginary. That's no good. So remember, none of this stuff we knew about when we started out. Okay? You start out, I erased it, but you start out with the square root of the sum of squares equals something on the right-hand side because it's the distance between 2 points and the distance between a point and a line. Same start out, same stuff down a few lines, except, okay, remember this comes in when you get, as I said, you get so far, it's exactly the same. Then you bring in these ideas, okay? So what do you think is going to happen? It turns out, if you look, whatever, I've reached page, I'm not sure what page, I can't see it through my thing, 8, I guess. Page 8 is where the hyperbola starts. And if you look at page 8, you will see that I define A and B and C again. How do I differ? Well, instead of E squared 1 minus E squared, it becomes E squared minus 1. So instead of 1 minus E squared, it becomes E squared minus 1. So there's a switch in order to incorporate the ideas, but now the E is bigger than 1, I have to have the square root of a positive number, so I make it E squared minus 1. This change is going to change some of the stuff that happens. Now, so if we go to the end of case 1, okay, case 1 develops a formula. If we go to the end of case 1, it turns out that for hyperbolas, the A squared plus B squared is C squared instead of A squared minus B squared. So what does that say about the relative sizes of A, B, and C? Well, C is the sum of C squares, the sum of squares is like a hypotenuse. So C is going to be bigger than A, and C is going to be bigger than B. I don't know whether, I don't know anything about the A and the B right now. So I can't say this anymore though. I just don't know. But the C is going to be bigger than both. Now, what I want to try to do is play the same game with the horizontal and so forth like case 1. And so if I try to draw the same kind of picture like I did right here, it's going to turn out, and one more thing somewhere, the H in this case, in case 1 is X naught plus C. Okay, the Y naught will be the same. So that's the other change that has to take place to do the same arithmetic we did before, the same algebra stuff we did before. Square root equals the sum, takes squares the sides and takes stuff to the other side and so on. Same stuff, except now I have an X naught, Y naught, and I have a D, but we're going to find out in this case, and I want to make sure I draw it right. In this case, it's going to turn out that if I have an X naught here and a Y naught, actually it's a point, and it's going to turn out that the HK is over here. It's hy naught or hk, it's the same thing because y naught is going to be k in this case one. So it's still the same height, but the h is going to be on the other side of the directrix in this case. Okay? And now, however, what's this eccentricity business again? Eccentricity is the distance over a distance. Now, distance of what? The numerator is 2 points and the denominator is point in a line. If the eccentricity is bigger than 1, then the distance between the 2 points is bigger than the distance between the point and the line. And that means that the point that is on this line that's on the graph is going to be closer to the d than it is to the x naught. We're still going to get this same kind of picture again. This distance here is now, as I say, if you look, this distance is the distance between the 2 points. This distance is between the point and the line. This is bigger than this. So the graph is still over here. But what was a center in the ellipse has now gotten over here. When you work this out, and you need to do that, but you'll find out that it shoves the hk to the other side of the directrix. That's kind of interesting. And what's the a and the d and so forth? Well, the d distance is still here. That's the distance d. The a distance is between here and here. So this is the a distance. That's between the point on the major axis and this hk. That's the distance. And what was the c? The c was the distance from the hk to the focus. If you look, the difference between these two is c. That's this distance across here. And what you'll see, I hope, is that the c is bigger than the a. That's what it's supposed to be. And you get this kind of a picture. Now, with an ellipse, stuff came back together. And we had the hk was the center. Well, now I got the crazy center way over there. Something, it's not going to be the same. I have no idea right now. I actually do know. Done all this stuff. Right now, it's like, hey, what's going on? Well, if you play around a little bit again and go over a distance over here, a, you'll find out there's a point over here on the graph. And there's another directrix. It's going to turn out that my problem is, again, space every place. I need to go the same distance over here to get that point. And I need to go the same distance over here to get the other point. It's going to turn out there's another focus, just like here. There's another focus, another curve like this, and another directrix. Okay? And so you're going to get another directrix in here. And it turns out that this graph, again, has two pieces. And what it's sort of like, is when you have the E is less than 1, you have an ellipse. When E equals 1, you basically get a parabola forever, but you only get one. In other words, this circle, the other half of the circle sort of like goes off to infinity. You can sort of think about that. This is like taking this thing and having the other half go off somewhere. And in the hyperbola case, it comes back around. It's like going around a circle this way, because the graph comes back. You can think of this as the other half of the ellipse, if you want to. Okay, so this when you change the eccentricity, it changes the ellipse into a parabola, and then it's like the other half must be off at infinity because there isn't another half. And there's only one directrix for a parabola. But when the eccentricity gets bigger than 1, it brings in a second half. So hyperbolas are broken, 2 pieces. And they're, oh, this is again halfway. And so once again, we have a center. Okay. Now, with the ellipse, I was able, in this case, to make an A distance from the center and a B distance and draw some points so I could draw my graph. Okay. This thing I had a while ago, I had x squared over 16 plus y squared over 9 equals 1. How would I graph that fast? Well, in this particular case, the center is here. I need to go 4 over here and 4 over here. This is a point on the graph. Go 3 up here and 3 down here. This is a point on the graph, and then try to make a circle. That's how easy it is to graph the thing once you know A and B. Okay? Well, in this particular case, okay, what we do is we make a rectangle. And because in this part, it's 13 after, I don't have time to develop exactly, but you make a rectangle and there'll be a certain distance here and a certain distance here, and that's going to involve the A and the B again. And this distance across here is A. This distance up here is going to be B. So you make a box that's A and A. In this case, it'd be minus A, maybe minus the number, but anyway, A on both sides, B on both sides. Okay. Then you draw a line through the diagonals. And that's actually going to go through the center. And it turns out that the hyperbola is asymptotic to those 2 lines. So now I didn't do it, but what's the equation of the case we have? What's the equation of a hyperbola in terms of the difference between that and an ellipse? And the difference is that you're going to have a minus. But you also might have a minus going the other way. In other words, when you have a minus, it depends on which is first and which is second. In 2 of the cases, the x will be first and the y will be minus. In the other 2 cases, the y will be first and the x will be minus. Okay? So the 2 hyperbolas we get look like these 2. Now, it's going to turn out that, and how do you know about these things? Let's talk about this one. How can I quickly know what it's going to be like? Is it going to be like this? Or the other case, is it going to be like this? Because when I switch things, it's going to make curves like this. So is this equation like this picture or like that picture? I don't know. So what I do is I let y be 0. First of all, there's no minus k and minus h. So center is here. So in this graph, the center is right there. Okay. What's the A and the B? I don't know. I got to think that out. Because I don't know which situation I got. That's what I'm trying to deal with. So how you know is you let the y be 0. And that says the x is plus or minus 4. So what does that tell me? Those are 2 points on the graph. And this is going to be the case where I have this kind of a graph. Okay. And so you just have to decide, see, for the ellipse, the bigger number told you which case. For the hyperbola, the bigger number doesn't tell you anything. It tells you, for example, in this case, I went over 4, so I'm going to go up 3. So it does make the rectangle. Whereas in this case, you're going to have the rectangle be longer this way than it is across. And in this case, I'm going to have a picture like this. And I'm going to have asymptotes that way. Anyway, but the A and the B, notice, oh, well, I didn't change them. But the A and the B, the size of the A and the B doesn't matter. It's whether the X is first or the Y is first for ellipse, for hyperbolas. Okay, now, I didn't want to develop all that because it takes too long to do, and it's 17 after, and I want to talk about something else. The next thing that happens in the notes, because the notes and the book do not do what I'm doing right now. The stuff I'm erasing, they didn't even talk about. So how did the book develop and how do my notes develop these conic sections? We said at the beginning of the notes, there's 4 different ways to do this. We've just gone through a way, and that is to take a directrix and a focus and work away. All right, we got a lap, we got parabolas, we got ellipses, and we got hyperbolas, and we spent 10 pages of notes or more. What's another way to do it? Another way to do it is to start out with 2 foci to start with for the elliptic case. The parabolic case turns out to be about the same. But in the elliptic case, you start out not with a directrix at all, no directrix, there is one, but you don't start out with it. You start with 2 points. And if they're horizontal, now we're in case 1 again. That was what we were doing when we had, remember case 1, we had a directrix that was vertical and the major axis was horizontal. Okay, well, you start out with 2 foci again. And once you start out with that, you can easily take half of the distance between the goals, and that's going to turn out to be H and K, although we may not know that yet. But what we do for an ellipse is we say, if I take a point out here, it will be on the ellipse if the sum of squares of the distances between the point in question and the 2 foci is a constant. And it turns out that the constant is 2a, where a has the same meaning as what we've developed here. But you don't start out with a, you start out with a distance d, and d doesn't mean directrix now, it means a distance. And it turns out that the sum of squares of the distances between is a constant. If you try this with a compass and a thing, we have different points. You measure these things like this. We have a point down here, you measure these things. And the sum of these things is supposed to be the same in all these cases. And when you do that, you will get, now what you'll get when you take this, I mean, this distance, take a point here, it's going to be over here. In other words, this distance plus this distance is a certain thing. Anyway, what's going to happen is you're going to get another thing like this. This is what the book does. Okay? So the book develops it, except the book assumes that we're starting, the book does an easy case. It says, let's suppose the center is 0. Develops everything. What does that mean? That's like this right here. When I have H and K are both 0, that's centering around 0. This is how the book does it. It does centering around 0 for a while. Then it says, now let's shift. Whereas I took the most general case, and then when I did an example, I shifted to the 0, 0 case. Okay, I like to see how bad it gets. And then when it's easier, I don't like to go from how easy to how bad it gets. Both ways are good. But anyway, so in my notes, I show you how to go from the eccentricity over to the other thing. Now, we don't start out with this definition. We actually prove that with the way I did it in the notes, that when you sum the squares, when you take a point, so if I have an ellipse, and I have foci, and I take a point on the ellipse, I already have equations for it. You can prove that this square plus this square is always going to be a constant. And therefore, you develop the second the thing the offer assumes, we prove in my notes. Now, it's 21 after. Let me quit the recording and just